Hey guys, this is Dennis Chow with SEI Security. I'm the CISO. This is one of our late night type of discussions, practical adversary and simulation and detection. So basically we're going to learn about signatures, how to create them, how to use a methodology for threat intel, and frameworks. We're also going to look at the red team side of the fence and look at what kind of ways we can simulate that, but also create the signatures accordingly. Um, this is roughly an hour long, and we're going to go ahead and use this, and it's roughly good for one CPE for most of your IT and security certifications. This will all be represented back in Apex Systems in their webinar in the future state December. This is a really, of course, of a test run and internal training, um, presentation at this point. So let's go ahead and get started on the deck side, shall we? Put that in presentation mode. There we are. All right. So just a general disclaimer from our legal side. Any tools, vendors, names that are mentioned are not considered endorsements or promotions. Everything that you see here is for educational purposes only, and really consult any other professional security teams, including yours truly, if you're wanting help on applying any of these methods and have not done any of these items before. Again, there's no guarantee that this will work in the future, and there's no guarantee of anything that we've mentioned here, only for the sake of methodology and learning how to do so with the existing techniques. So our learning objectives I mentioned a little bit earlier and alluded to is that we're going to use threat intel and frameworks to methodologically create a simulation for adversaries, specifically their TTPs. We're also going to learn how to create and modify open community signature formats. So IOCs, Snort, Suricata, Sigma come to mind. So we're going to create these that just are available for sharing and easy ingestion into your security tools. We're going to demonstrate 5 different attack scenarios that we commonly see in all of our pen test engagements and purple team engagements that are across multiple industry verticals as well as sizes of organizations, so small and large, Fortune 500. So really interesting stuff. And we look at how to apply some of those methodological tool set signatures and how do we actually detect some of those in little pieces that we can create signatures out of. So let's think about that. So our scenario is that we have our top 5 issues identified in our engagements. We have a victim host, which has a Windows 80 domain of 2012, 2 workstations, Windows 7, Windows 10 accordingly. Our attacker host is Kali. We have Infection Monkey, Google Cloud, Compute VM, and generally we hope that you understand networking concepts already, general security concepts and terms, and are comfortable with CLI-based tools. So not a huge ask. So almost anyone can really do this with enough time and effort. So here's what the network looks like. We have established, for whatever reason, a foothold on the network, either based on proximity close to us, um, or via remote exploitation. We've maybe compromised another portion of the network. We've gotten in somehow. And we're going to attack other hosts on the network, which lateral movement is a huge deal. And a lot of organizations, not just small ones. Large ones have visibility problems too, based on resourcing constraints. Again, we have our Windows 7 32-bit host, not 64-bit, 32-bit, because we see that a lot more on those networks still. More so for IoT embedded devices. Windows 10 Service Pack 1, 64-bit. Windows 2K12, R2, which is a common Active Directory one, that might be to 2016, coming up really soon due to the end of life. And of course, Infection Monkey, which is something the blue teams might use, but you can also use it as a red team or two. We're also going to assume that you can create connections outbound to the internet, and we will have a Google Cloud Compute VPC instance in there with our attacker VM to listen in as our shell kicks back on one of our demonstrations here. You might say, I have a tool for that. We have a demonstration automation use cases via Infection Monkey. There might be Red Canary or whatever else you want to use. But every tool has their pros and cons. Every tool has their strengths and weaknesses and their scopes for how you should use them. And so you can't exactly rely on everything in one tool set, right? You need to be thinking about other fail-safe issues and manual methodologies just in case something happens. For instance, Infection Monkey, as we'll see later on, has a very distinct signature. And if you don't have authentication, sometimes your exploits can actually fail and don't really work. It may not give you the same picture that you would get from an actual pen test engagement. So just don't rely on automated tools ever, right? You need to actually use your analysis and capabilities, and tools are just that. They're just there to support your analysis capabilities. With that said, let's think about our methodology. First and foremost, top-down and adversary simulation methods are what we're really looking at. Top-down as in, yes, we're going to start with top TTPs, but someone else has thought about that for you. And so what you can really think about is examine threat reports and playbooks from trusted sources. Overlay the modern attack framework from the IOCs that are from those playbooks and reports. And ensure you have all the log and network sources for visibility to actually create those simulated TTPs. You also want to validate log and network visibility by simulating them, right? Using the red team skill sets and reproducing those IOCs based on a variety of techniques. MITRE ATT&CK framework will sometimes list them in their actual stages. And of course, you want to perform automated and/or manual analysis of those logs and traces to create more signatures and more enrichment and in-depth to your security program. So again, you don't want to start with hashing and IPs and domains because everyone can have that. You actually want to start with TTPs because that is something that someone else from a security researcher has done and you're not making the best use of it. And so let's start from the top and work our way to the bottom versus working all the way from the bottom and trying to revert, work backwards towards the top, right? So let's think about how we're going to do that. Some threat intel to consider is the Verizon data breach report. These are just one of many areas that you can look at. And so let's think about what our perpetrators look like. Who's behind the breaches? Most of it's going to be external based. Um, who else is going to be itemized in here? We're also going to look at um, organized crime groups, so a lot of ABT. 30% of that seems to be inside a threat case. And we also look at the top three issues here, right? Malware, social engineering, errors, and casual events. So, possibly related to social engineering or some other configuration errors, and breaching featured hacking, so exploitation, misconfigurations of hosts. There's a lot of things that could go wrong with that. So let's think about how we actually map that closer. In the Verizon data breach report, also in the same figure, I think in different figure in a different page, it actually lists all these that have come and gone over time for the last 5 years. And so malware, scrapers, social phishing, Trojan hacking, more malware, ransomware, stuff like that, error and misconfiguration. This is all pretty straightforward. And this ultimately leads to a combination of vectors that you should think about, which is mostly going to be social engineering, um, exploitation, and possibly traditional external hacking based on lack of patching, authentication issues, etc. And that has actually phishing still being among the top. Um, and stolen credentials and misdelivery, misconfiguration being, supporters of this, right? RAM scrapers are becoming less of an issue because you're looking at flat files and ransomware is going back up in an uptick here over the last year. So some more appropriate log sources, basic coverage first, right? Think about your critical applications, right? Look, all the ones that handle compliance data, regulatory, critical data, transactions for your organization. Windows hosts enable the audit detailed logging and collect the minimum of the security events. And if you have the resources, please do the PowerShell history as well. For Linux hosts, you might want to think about the syslog daemon and get the bash history, varlog messages, and Debian and Ubuntu type solutions, forwarding over to your SIM. Network sources, right? Firewalls, routers, switches, hypervisors, etc. Everything else that can give you that north to south kind of visibility mix, right? So edge to the inner circle to your trusted zones of your networks, all that should be covered wherever possible at the absolute minimum. So how to use this top-down method. So let's think about our MITRE ATT&CK framework. When we look at the playbook from Palo Alto Unit 42, they created a really nice playbook. All these links and everything that we're going to mention here is going to be at the end of the presentation as well as in the deck that's going to be handed out in the webinar slide. So, we're going to look at Maze. Maze is interesting because it's been known to target the U.S. Through May 2020. I believe it's first found in May or the summer of 2019 and discovered and publicly discussed. And it's a ransomware. So it's based on actually profiling of your data and your ability to pay, and it'll increase and decrease that based on whatever it thinks your specs are and how great your data is worth and how much you have invested into your hardware. So if you have a home machine, it's going to have a different level of ransomware requirements than an enterprise. And if it finds PI, PCI, so it's really contextual. It's pretty neat. And it has the known IOCs of using the Fallout exploit kit. When we run the playbook over the MITRE ATT&CK kill chain framework overlay, we see a bunch of indicators here that Palo Alto Unit's 42 research team knew about. So if you see 0 indicators here, it doesn't mean that it never used it. It means they know they used it. They just didn't have any IOCs that they wanted to publish or they don't know about from the campaign all the way from, I believe this one was April 2019 to April 2020. It knows 24 IOCs publicly released for spearphishing, external resources, logs, disabling security tools. So, we're going to focus on a little bit of these, but it's really up to you as a defender and as a red team simulator as well, or if you want to call yourself a purple teamer, you're gonna go ahead and try to use some of these playbooks because they're really nice, and they've spent a lot of time in there. So, why start from the bottom? We want to use the easy button, start from the top. Made simulation. So, look at external resources. That's TDP 1133, and they used their IOCs included a lot of Citrix and RDP. So where are you going to get these log sources from? Well, load balancers, WAFs, the actual endpoints themselves if you're doing direct port forwarding, which I hope you're not. And for the RDP, you're going to have event ID 4624 from a Windows standpoint, type 3710s, which are respectively for their different types of interactive logons and or network-based logons, and sometimes app event ID 9027, which is a console-based related event. And this is kind of what it looks like from a raw event log format. Kind of neat. Um, so that's something to really think about there. Another TTP and a way of getting about it is, again, PowerShell, get event log and filter on what you're looking for using the where clause and select object first 5. You can actually get what our app event ID that we mentioned earlier with 9027, right? And so you have your index timestamps and whatnot, and it gives you that good rich full information from an object standpoint if you want to dump it. We also saw with the TTPs that it disabled security tools. Security tools being this list here from Palo Alto's research team, and it has a pretty typical list of what a lab might look like for reverse engineering. Procmon, ProcExec, Sysinternal Suite, the x64 debugger. And so what we're going to have to do is we're going to have to simulate what the equivalent is that they may terminate. And so we'll see that in the upcoming slides. But we might use task kill, and a security event ID of 4689 is to terminate that task with procmon 64 to exit. So we could use WinAPI calls, shell commands, and your Windows log sources will use 4689 to actually denote that. So we're going to use task kill to simulate a little bit of how that might look from a basic shell command perspective. 4689, right? We want to filter that again based on our get PowerShell command, and we're going to have to go ahead and run that. And you can see that I've already killed procmon based on its process name, not ID, and you should see a successful termination of twice, right? So that's pretty neat. So you can always think about that in terms of, my first simulated IOC here. Now, you should see procmon 64 exits roughly at the same time after killing the task. So you might see double entries related to procmon as well as task kill. So when you're looking at correlation of events in your signature creations and other detections, if it's using the task kill format or even a WinAPI format or .NET, whatever you're going to use, it's going to have the kill-based exit being executed and then returning after you've killed procmon, and procmon's process ID dies. So you're going to have two events in one to actually create the actual event of it disabling the tool, at least for that one tool. Another way of IOCs inside the playbook was TTP 1027 and is obfuscating of files. The IOC pattern that the Unit 42 found in their sampling was the directory path of recycle bin. It had the word decrypt-files.txt in there, and obviously you could create this via interaction, but you're not going to do that. Malware is not doing that. So one way to do so is COM objects. PowerShell has the ability to do so. It could be in the script, or it could be in runtime in memory. So we'll simulate that. We created a COM object here in our PowerShell item. We have namespace, parse name to create the handler of the name, and then we're going to invoke delete. We'll touch that and we'll delete that to recycle bin. And notice here, when we use the COM object, we don't have that when you look at it in a directory from a command line perspective. But what's interesting is you can see it in the Windows shell perspective. So that's an interesting artifact difference. And of course, if you had If this was the methodology for the original attacker or the ransomware or whatever you might want to use for Maze, PowerShell would be the way you actually grab that script here. So let's think about signature development, network artifacts, leveraging secure Suricata and Snort, right? Those are pretty important. Now, we're not going to get into an argument about encryption or decryption. This is assuming you have that visibility, even if it's decrypted. There's a lot of privacy arguments around that. That is for a completely different discussion. But think about how these signatures work. Suricata and Snort format's pretty open. Everyone kind of knows what it looks like. And we have a WebDAV connection here, which is not necessarily normal. And we grabbed a template from that was WebDAV related for Java, excuse me, and we're going to go ahead and create and modify our own. So instead of alert HTTP, which is Suricata, which does layer 7, sometimes those parts just don't necessarily work, so I'd like to use TCP. We'll have our source port, destination ports, whether it be variable or the really static name here, our message for what it looks like, and a flow establishment to the server because we're talking about grabbing something, getting a process. And we have prop fime and content user agent string information here with a 1 million and 100 ID just to kind of not overlap in Suricata there. And that's all it really is. You don't have to get any kind of crazy with it. The more specific you are, the better the tuning is for your resources of your IDS, IPS engines. But from an open source intelligence sharing perspective, this is not terrible, right? You have your main keywords, um, and it could have multiple false positive fires, and more so than it needs to be, depending if the stream was not properly set or you're doing fast alerting without a little bit more constraints around this. And this is pretty intensive because it doesn't say to stop somewhere or look at only HTTP URI headers and stuff like that. So it's more tuning, but it'll fire, right? So that's ultimately what we want to do. So that's one way to actually display network artifacts and create signatures. If you want to learn more about Snort signature and Suricata signature creation, there's plenty of cheat sheets out there, and I would recommend doing a Google search on emerging threats for what you're looking for first, and try to utilize that as a template. Again, easy button, practical adversary simulation. If someone else has thought about it for you, modify, make it your own. We're also going to look at signature development and network or log format. So if we're creating MS17010 here, which is eternal blue or eternal whatever you want, double pulsar, some of the artifacts might include forensic host ones. So creating a service is not really a good sign either. But here we also see a buffer overflow. Which one do we use? Well, we could use actually both in this case. And so when we look at network versus log artifact for a system level IOC, maybe open IOC might come to mind, but depending on what you have logging wise, your SIM could actually do this for you too, right? So let's think about what we're going to use. And one thing that you could use is the Sigma based correlation rules, and which is kind of an open standard. It's really become more popular in the last year or two. Back in my day, yeah, I'm an old person. It hasn't been around for very long relative to the rest of the security industry. So you have curators, your Elasticsearch Stack, Splunk, and you have their formats. And so we're just trying to do the same thing like Yara rules or YAML rules or whatever you want to use, and just describe the actual nature of the keywords and content and what the conditions are in a more structured format that can be converted easily. So uncoder.io, which is by Sock Prime, which is what they created the community for signatures, rule sets and conversions to the Splunk equivalents and whatever. This is an example of a buffer overflow for FTP. So you can obviously modify the keywords and say what the conditions should be. And here's what you might see in the Splunk equivalent if you had that level of logging. And again, that's the actual URL if you want to try it yourself and modify templates accordingly. So a really good way to showcase SIM-based correlation without having to be exact to a specific technology stack, which is really nice. So consider using Sigma. Or you can use system logs. So one of the other things that we do is think about what we just saw earlier. We're ServiceNow, not ServiceNow, service creation, and we're creating services, right? So Windows service installations, installation install, event ID 70454697, and we're using these keywords here as our content, right? The equivalent of you seeing WCS service, dump serve in the network stream instead. But instead of having those keywords as part of your service name, you could actually make more randomization of regular expressions potentially here. Our equivalent here in the Splunk world is the same thing with ORs based on the log source index here. So signature development, again, also depends on where you want to target, right? So we're going to look at systems, right? If you're looking at, instead of binaries and just YAR files, think about OpenIOC formats. So, one of those things that you look for system level, instead of binary level, system level IOCs, right? It might be Mimikatz. Mimikatz is pretty important. And I'm going to try to dump LSS secrets. This is from Covenant using a .NET payload. And it's using all these calls via these imports here, as well as these subroutine functions and these types of parameters. And those could be keywords in there as well as looking at the memory snarfing and the buffer. And that tool to do so with this is called API Monitor version 2. Is in alpha by Rohit Labs. Pretty nice, commonly used in a lot of reverse engineering efforts. So how do we actually get that to an open format that we care about? So again, EDR forensics, OpenIOC is a nice kind of methodology to do so. IOCbucket.com has this online editor, so be careful what you actually have. So remember that is going out to a third party, so you may want to use like Mandiant's offline on-premise tool set. But remember, OpenIOC, it didn't really catch a lot of popularity as much as they would have liked it, but it's a really good format still to actually showcase your IOCs and import and ingest into other tool sets. Tanium uses this, so OpenIOC has a compatibility, so you can use ORs and ANDs and really specify what you're going to have in your arguments. So we having for like a PowerShell payload and running LSAS for our Mimikatz, you might have file name binary on disk. It might call and import like sekhostdll that you saw, as well as the LSAS attempts at the hooks and the routines that go with that. So pretty straightforward, easy button again. Consider all things in terms of your threat intel sharing and adversary simulation and detection. So it's time for the demo. We're going to demonstrate the top 5 findings that we commonly see in our test engagements, large and small companies. We're going to showcase Infection Monkey as part of an automated simulation too, but it's not going to get everything that we're looking for. So that's why we're going to use a manual approach. We commonly see Element or NetBIOS broadcast is still enabled, so we can use Responder, capture those hashes like NTLM-v2 by default, and relay them out to somewhere else. Or we can crack them ourselves depending on how much time and resourcing we have, or how much we know about the password potentially too, right? Look at password audit policies, password complexity policies once you do your first pivot. MS17010, sorry, Eternal Blue, Double Pulsar, as we mentioned, Windows servers, Windows 7, embedded and 80 and 32-bit editions are pretty common that we see for customers. So this could be healthcare. A lot of issues with the embedded devices are modality machines or embedded Windows-based other healthcare like CT scan type of devices. And a lot of vendors hide behind the FDA review process and they're not going to patch it or whatever it may be. Well, the FDA gave guidance back in 2016 when the whole cyber threat intelligence sharing and framework requirements were being created. And they basically said if you have commercial off-the-shelf tool sets, libraries, software as part of your base OS, that could be patched without being a review process as long as it's not changing critical functions and use cases towards the unit's primary function. So if it's a CTCAN device, unless it's changing a huge workflow or the use case of how the technician will use that device, you don't need a review process for the most part. So patching MS17010 should not be a problem, but many vendors push back on that. So, you as defenders need to be able to know what the laws and guidances are and push that back onto the vendor and really keep, securing your network. We also find that there's no egress encrypted visibility for SSL, TLS, SSH, and a lot of common trusted sites who they might do a bypass if they're using encryption and decryption proxying at all. 365, Google, Azure, AWS, all those are different trusted items. Even CDNs like Cloudflare and Akamai are commonly trusted, and just because you're ignoring that traffic, you're not seeing anything, and you're not inspecting it, you're not making policy actions based on that. So we're going to use like Netcat's SSL feature, which is kind of cool. When I say Netcat, I mean Ncat's Nmap version of Netcat, which is a It's kind of a Gen 2 netcat here. We're going to send it out to Google Cloud. Naturally, we don't have a real IPS in place, but we're going to simulate it so you can see what it looks like. Log sources are not locked down to ACLs or client-side certificates, including encryption. And you create your own incidents, right? You create all kinds of false positives and generations, and you can have the whole SOC team looking at a completely different incident that doesn't exist, a ghost incident, on a different portion of the network than the one you're attacking. So that's really useful to just jam stuff and things. You might even have to make them drop EPSs. So depending on their licensing, you might actually have them dropping events, legitimate events on their SIMs, which is also a huge issue from a denial of service standpoint. We're also going to look at improperly applied Active Directory delegate permissions, so get ACL, set 80 account password, and we're going to look at an overly permissioned help desk user. So let's go ahead and get started on our demonstration here. See our messy desktop. Okay, so we have VMware, all these different items installed, turned on. Let's go ahead and sign in and get started on our front here. Okay. So I'm just going to go ahead and make sure we are cleaned up from all kinds of nice stuff. And bear with me on that. There we go. So we've run this demonstration obviously before. So let's go ahead and get our dump started. And we're dumping S0 for just all frames. All bytes in our frames. And we always want to run this just for the sake of creating artifacts from a network standpoint. Go ahead and run Wireshark as well for the sake of being able to look at it visually right quick. And we'll let that stew for there too. Let's go ahead and run our Suricata update to make sure we're on the latest and greatest Suricata. Emerging threat, open rules, if I can type. And we're going to go ahead and create a attempt directory for our web dev server to deliver our payload laterally or externally to the network. So we're going to go ahead and create our directory that's globally writable. We have this little tool called WSGI DAV, and we installed it, and we have clear text, anonymous usage, so you can actually run it over a TLS certificate, but we're not going to use that for this purpose here. Our signatures are updated, so let's make sure that we have our web dev rule that we kind of showcased earlier. Let's make sure that we can actually run it. And we have a beacon that we already made for web dev, and make sure that we actually have our use here. Alerts 28, that's a good sign. Let's delete the log files. Delete the ev.json. Cool. Downloads, demo. All right, cool. So first things first, let's showcase Infection Monkey because it's already running. We can shut that down in a bit. And that's running on its separate OVA right here. For the most part, it's pretty simple to set up, configure. It's quite nice. It has a lot of stuff in the minor attack framework that pretty limited, but still free, right? So take a look at that. We have our exploits that you can see here and turn on. Most of the time, you're not going to get good exploitation with this tool set unless they're credentialed based. So you can let it do its brute force thing. And of course, you can blockade a number. We're not going to scan. It'll scan itself unless you block it. So 145 is the Monkey Island, and 134 is this Kali and Linux host. And we go ahead and block that off. And of course, you can use post compromise commands and have it run payload if you wish, and do all kinds of crazy stuff. And you have our dropper types and dates and abilities to do a lot more fine tuning. It's kind of cool in our kill time. So let's go ahead and run our Monkey on the Monkey Island that we have hosted on the server, and it's going to start doing stuff, right? It already found stuff. We've run this before. It's ran scans before, but it hasn't been able to exploit anything, and it hasn't never created a tunnel because we don't have the right credentials, and it's not going to brute force the way you're looking for. Because it's been ran before, we have our timeline of when it was run, what was run, and all kinds of interesting stuff that happens that goes with that. And you can see that in the packet capture that we have here. Now, the interesting one, because we're running that infection monkey scanner, um, it has a distinct IP address, essentially. Not IP address, but it has a distinct signature, and it does a lot of RSL packets, um, which are kind of interesting that essentially are radio signal link that transports, that runs over the TCP layer. And that's pretty unique to Infection Monkey. If I turn off Infection Monkey now by killing all monkeys, which is kind of horrible sounding to be honest with you, kill all monkeys, that RSL traffic will stop. And so you can actually create signatures based on RSL alone. Of course, see here, no more RSL packets. You know, we start seeing the other broadcasts and interesting packets that we're doing from a web DAV perspective if anyone's connected. Okay, so we kind of showcased a little bit of that. Let's go ahead and start off with element R. So we see this, we might be seeing element R already, or maybe NetBIOS. We haven't really seen anything yet. We might have to start triggering UNC files here. Yeah, we might see this as Windows logs in. So let's go ahead and log into Windows 10 here. I'm a help desk user, I'm just doing my thing. I'm a local admin because I help desktop support people from, as well as my part of my functional duties. A Windows 7 host will have a user, maybe a user one victim. If I can remember the password. So I'm not a local admin on this as a user one. I'm also tied to the domain. All right, so I am a local admin of this, but I'm not a domain admin. Okay. One of the first things we're going to go ahead and do is we're going to go ahead and make sure that we can start responder up. Okay, so let's go ahead and start responder. And it's responding. It's going to go and inject and poise stuff. It's going to initiate attempts to get everyone to talk to it automatically for us. And NetBIOS name services are enabled. We're listening for events, and nothing's really happening. I mean, I guess we could go talk to our domain controller and get the net log on and look at this path and sys value, and we don't have anything access to it. So no group policy preferences. And look, it's already profiled stuff, right? So in an enterprise environment, you can see more of the UNC going on, especially when you have DFS enabled in a lot of places. So we have our WPAD. It's trying to inject things. It's not really working. We're not grabbing credentials yet. That's lame. Well, let's go ahead and try to, for whatever reason, we're going to contact our Kali Linux box because of social engineering and said, hey, help me user, here's my UNC path. I can't log in. Can you log in? Maybe I can, right? And whoops, it doesn't work. But hey, guess what? I captured all your Intel MV2 challenge and handshake, and well, that's enough for me. So we'll go ahead and close that. That's already created inside a log file inside responder. So as soon as I capture that, I can start cracking. And because we've already done this before, I've already copied it into our demonstration here called called our hashes. So we're going to remove .responder.pot because we've already ran that. We're going to remove the JSON and the .log files here. Much cleaner. Okay. Let's go ahead and crack our files. So we know that based on our, for the sake of timing, we're going to go ahead and say that we know that the pound support foobar 123 exclamation point is our password. We're going to just do a mask because we already know the first half of it, and we're going to just leave John to crack the rest of it. 123 exclamation point. And because it has salts and stuff like that, it's still going to take longer than you think. Let's go ahead and run that. It's going to run. Let's go ahead while it's running, right? let's go ahead and run our next use case, which is our Windows 7 vulnerable external blue, even though it has Service Pack 1. And how we're going to do that is go ahead and we're going to use our exploit that we found, not necessarily from Metasploit, but an external ones. Because the problem with Metasploit modules is that it's meant for 64-bit, and as you can see here, even in the search exploit DB, you're going to see that everything is 64-bit focused from a prepackaged trusted standpoint. So we found someone else that found a really nicely made set of exploits that go against a wider range of OSs, and specifically 32-bit. And so that's what we're going to use right now. This is all in Python, so it's going to use an authenticated SMB session because we've assumed that we've cracked these passwords already, because we already know. We're just running John for the sake of showing you guys. And as you can see that we have a numerous set of proof of concept exploitations that's going to be wrapped into the send and execute Python script here. And if you really want to see it, we're running a authenticated session. Really nicely done. Whoever wrote this is, really done their homework here. Okay, so we've already entered in our Cortex password that we've already cracked from here, supposedly, in this option. And we're just going to go ahead and run it. And remember, we're capturing the packets, right? We're capturing everything inside Wireshark and TCP dump. But first, we're going to go ahead and create our payload. Venom, because it's 32-bit, we can use Chicago Nye, and we're going to create our listener, payload, and stager information. We're also going to go ahead and start our listener. MSF console, R, and our x86 stager resource script. Still cracking. All right. Okay, so we got that binary saved in a 64-bit solution. If you're still creating the MSF Venom binary, you can always use the AES key encryption enablement, and we can go ahead and run that against our stager. And it started. Now remember, you're gonna see something kind of interesting. So we're gonna use shell reverse TCP instead of MetaInterpreter. So it's gonna drop us in shell. We could always get system if we wanted to use MetaInterpreter using its standard built-in methods for Kiwi and Mimikatz. I'm gonna center, execute, and payload, and it's created a service. All kinds of interesting artifacts will come up on our Windows 7 box. And if we look at services here, we should see bad things happening in general. Not from a user standpoint, but from an administration standpoint, we got weird services popping up here. What was our called? This one was called VR something. And for whatever reason, we can't see that in this one, which is kind of interesting. Usually it pops up. Oh, here's one. Started this one, so maybe it clobbered it or something. So, oh yeah, UT. VR is the executable payload, sorry. UJ is our service name, and it started, and it got a response, and it just says done. And we got our shell opened up, which is a general command shell, and we have NT system authority on it. Woohoo! Because we're not in a MetaInterpreter, we're not going to try to go get system or nothing like that. We just wanted to showcase that. But what's more important, when we caught the information right here, we should get the SMB authenticated stream, and we should see the great buffer overflow in one of these streams here. So SMB contains, and we can always use 909090. Oh, no NOPs. Okay. There we go. Well, we'll see our buffer overflow here is A's. So we're not using an ops sled. We just have a straight up buffer overflow. Very cool. Well, if we're, and those 41s should be pretty common to a lot of you. So we should also see the MZ because it should in the same stream send the binary file. And look at that. That's our binary file that we just generated with Venom. Okay, that's going to be in our stream. That will obviously trigger some bad stuff going on later on. So we saw RSL already. We saw the buffer overflow MS-17. Well, let's think about our capturing of going out to the cloud. Well, we're not capturing via Kali, so we're going to go ahead and just kind of showcase what it looks like to go ahead and just start up an instance in Google Cloud. So we have a very small box, and we have firewall rules. We have a VPC. It's just one little box coming in and out. I'm going to go ahead and start it. While that's starting up, let's go ahead and create our portable. All right, we're going to use our Netcat portable with our stolen credentials, and go ahead and get that ready to send a reverse shell out for us. You don't have to be an administrator to run it, but because we're administrator locally here, it already sent us to the administrator for shell. All right, well, we're not going to use Windows 7 anymore, so we're going to shut that down and save some resources. Let's see if Kali finished cracking our passwords, and it's still chugging along. We're about a quarter of the way in. All right, so we have our VM running. Let's go ahead and connect to our VM via the web interface browser, and it's going to create a nice little PuTTY equivalent session for you. And while it's connecting and transferring keys, whatever it's doing, we'll go ahead and get the commands set up. So netcat or ncat, sorry, using IPv4 only as our route, very verbose. The SSL switch is really nice. And our 443 is going to be our port because we're not inspecting it. All right, cool. So we got our Google VPS going on. Remember, Google GCP is free for a very small Linux box. You're not going to be doing crazy hacking on this, but to receive a shell over a trusted IP, I mean, you practically have every month for free, including the storage, which is kind of nice. So we're going to curl ifconfig.me, see what our WAN IP address is. Ifconfig.me is a site, and we are 34 something. And I believe I already created the firewall rules and enabled them for our lab here. Let me double check on that and make sure I am still coming from 135 from a 98 address, and boom, we are good. Alrighty, so before we create that, we're going to go ahead and create our listener on the catch it on the GCP side, and cat LPK. Again, you have to specify SL to receive it on this port. Let's go. And what happened here? We are from the context of the user, of course. And as you can see here, it's not perfect, but it's an easy shell to get back. And if you're not going too crazy with it, you're not going to go ahead and have it crash. So just wanted to give you a showcase of the dangers of trusting blanket FQDNs and IP addresses over that without doing your performance inspection. So obviously we didn't capture that. Even if we did, it'd be all TLS encrypted or SL encrypted based on its stuff here. We're still seeing a bunch of syslogs being sent, forwarded over to our Windows 2K host. Speaking of logs, right, we're going to look at what we're talking about is, for the most part, not using ACLs on your log servers or log ingestion areas for indexing. So the problem with that is, as you scale up, it gets really difficult to create firewall rules, stuff like that. And so a lot of enterprises don't check this. And so this is what normal looks like for our network, because we're still sending just Windows security event logs from our different hosts, including Windows 10, Windows 7, and to itself. Well, now that we know that what that normal looks like, let's look at Kiwi logs. And of course, to do real spoofing, you're going to use Scapy or something like that. But we're going to send it to our SIM, which is our domain controller here. And we're going to simulate all kinds of malware infections, some random junk. And if we refresh that, it should start sending all kinds of crazy going on. Damn, that's where it is. Just sending all kinds of fun, right? So we're sending all that stuff out and bursts, and that's just malware infection somewhere else, all kinds of corruption. And actually, we're not spoofing our syslog UDP packets themselves, so they're still coming from the same source from Windows 10. But if you did that for real, you wouldn't know where it came from because it's all UDP, right? So no integrity there. I could cause my own incident elsewhere and really start confusing analysts for a lot of fun here. Okay, so we just kind of showcased that, a quick and easy one. We're going to look at 80 permission, delegate permissions now too. So depending on your setup and environment, we see this in large and small environments, so don't feel bad if you're a small environment. Default domain admins group inside the user's OU, and they're delegating control to help desk users to reset passwords. And a lot of, depending on your configurations, whether you upgraded Windows Server 2012 or not, or you did that um, from a clean install or running it, an older version of your domain controllers, you may have domain admins already delegated or have inherited permissions, which is not a good thing. Typically, you don't want to have inherited permissions, but we're going to enable that as a bad practice because sometimes different security tools or um, other enumeration tools for Active Directory might have enabled it by accident. In our case with Server 2012, it's going to disable that on every boot, which is a good sign. But if you don't reboot your domain controllers very often, you're going to have that opportunity window for an attacker to have that server. So we're going to enable inheritance on domain admins as well as the domain admin 2 user, just for the sake of our demo purpose here. And I'm going to say, hey, help desk person, we want you to have the ability to reset passwords. Yeah, that sounds pretty good. Because it's inherited across the OU users, across everything inside this OU, and we have enabled that explicitly just for the sake of this purpose demo, we are now should be able to, from a help desk standpoint, even though we're not domain admins, reset the password of a domain administrator. Local admin running RSAT tools. Now, usually you're going to use PS Empire, which is now defunct, no longer supported. So you might use, PowerView, which is part of PowerSploit, the predecessor, PS Empire, maybe an additional scripts with Covenant, and you might import that into your session for when you're pivoting from a, from a compromised workstation. But we're going to use RSAT tools just for the sake of simplicity, showing you guys what it looks like, not necessarily from an attacker point of view, but from how you should see those artifacts in the logs coming in. So this is how it's happening here. All right, so we've already set those permissions. Let's go ahead and get um, our distinguished name, which is the string here, and we're going to see what our permissions look like. So let's see that we make sure we have our password reset permissions delegate for sure. Good, and we can change it on everyone. Inherit from parent, that's not good, right? Special is usually to make sure that you actually have delegate permissions, which we have special access to all administrators and everything in that OU, which is a very good sign. Notice that it does not show domain admins by default here. So we just explicitly enable inheritance for them. Who are the domain admins? Well, knowing that we have help desk delegate permissions, domain admin 2 looks like it's beefy for changing and resetting that password without having their password. So we can do so via delegate permissions by resetting the password via PowerShell set account password, and we're using a secure string by parentheses, which is your backtick equivalent in Linux, to pound support foobar123 exclamation point, which is the same as our help desk user password. There's no error permission issues here. Let's make sure that Calais, did John already finish it? And it did, yay, okay. We'll go ahead and close that. And just for the sake of showing you guys, what that looks like, well, we can always sign in interactively, or we can run a command prompt as another user, or we could just sign in as the domain admin. So let's switch user real quick, switch account, just for the sake of a nice showcase. Domain admin 2 and support pound support foobar123 exclamation point. Oh no, we're logging in. Yay, domain admin owned. All right, cool. And that's all from what? Remember our first use case, grabbing the help desk credentials that had delegated permissions from LMNR, right? Or just social engineering your way to get someone to click on the UNC link with respond running. Well, that's not good. Let's sign out. And let's go ahead and run, a bonus material like Covenant. I wanted to show you guys Covenant before we, um, move onwards to our last item, which is looking at the actual Suricata PCAP. And I wanted to show you how much more appreciation Windows 10 has from a security perspective than Windows 7 ever did. We're going to go ahead and run, grab the WebDAV file that we have in Kali, right? I've already mapped it just for the sake of mapping it. And oh, I never copied. I never copied the payload. So 1 second here. So I'm going to copy. Have my little cheat sheet here to make things faster for this demo. Copy everything to the WebDAV temp folder, and we should have that. There we go. All right, so I can access just like with HTTP. You'll see that in the PCAP. We'll copy over PS grunt, replace it, and really here, this is what the payload looks like. And anyone that's ever been a defender knows that that does not look very good. That doesn't look legit at all, right? And it's a hidden window too, which is kind of funny. It's not really encoded whatsoever, so it just looks like a nice thing to do. So let's look at Process Explorer 64-bit, right? That was something that Maze was trying to turn off from a ransomware perspective. I'm going to run it anyways because we need to see what's going on. I'm going to run our equivalent from a batch file, and look at our nested tree issues, and we have it showcasing for us from what we had earlier, including our parameter. So that's how we really find it from here. We could kill and suspend or create a memory dump of it, but we're not going to do that. Let's go ahead and use API Monitor. API Monitor version 2 alpha is from Rohit Labs. Really nice, really nice to have. And we should also see, we never ran Covenant. Oh, I am so sorry about that. So let's go ahead and run Covenant now. Hopefully that stager, that grunt as they call it, is still going to run and connect to us without failing. And unfortunately, the PowerShell process no longer is applicable, so it looks like it filled out and killed itself. So we'll have to run that again. No problem. All right, Covenant is now running because we already downloaded it. It's a browser-based item. We can just kill the Wireshark for now because we're going to see all that in our first packet capture that we captured and are capturing right now in the live demo. So let's go ahead and run Covenant, log into the portal, and as you can see, it's just like every other nice framework. You create a listener to it, and that listener can create launchers, and launchers we're using is obviously PowerShell. The interesting about the launchers, though, it's all .NET based. So whether you generate via PowerShell, MS Build, or the equivalent of how you can do it, it's all based on .NET 3.5 and 4.0, which is essentially you're going to need Windows 10 and higher by default, because Windows 7, maybe even 8.1, Windows 7 actually just has Windows 2, PowerShell 2.0. This, whether you create a binary or you're using this payload, this is the source code that you can use to extrapolate IOCs from by itself. So if we have our listeners, it's always listening to 8443 for the sake of non-conflict here, but in the real world you'd use a pretty common port. Let's run that payload one more time, and we should see PowerShell come up because we're not running it. We're going to start monitoring it based on .NET libraries as well as networking libraries for WinAPI. Boom. We have all these imports going on. We haven't really done anything with it yet because it's already established something, so all the networks are gone. In terms of what we didn't capture initially, bam, we've got our helpdesk user 1. And we have our stager which we can interact on. So very nicely done here. Very nice tool. And as we open this up, let's go ahead and say, who am I? And it's going to send and receive packets and all kinds of great stuff. I'm also going to go ahead and shut down Infection Monkey. free up even more resources to make it faster. So help desk user, all right, so we're going to go ahead and try to, this is similar areas where you can dump your PSN Power type stuff to import additional PowerShell based items. So we can go ahead and bypass UAC with the grunt, which is going to fail because Windows 10 actually has a lot more security than Windows 7. It's tasked and queued in there, so we're also going to try to do, let's go ahead and try to just get LSAS secrets. And failed to bypass UAC, failed to get, I'm sure you can, the same will happen when we do get system with it too. All that's queued, it's going to fail out and error out. And let's see what, maybe cats is loaded obviously, and it failed to elevate, can't dump secrets, can't get system, even when we're admin, right? Even when we're a local admin. And what we've found here, we should see a whole bunch of, there we go. We should see a whole bunch of LSAS attempts at trying to get, all the nice little items that we just try to do, and it's showcasing us that this is kind of what it looks like on the Windows API backend for these imports. So you can create IOCs just from this, from our simple LSAS and get system dumps already. So that is certainly something you should consider from an open IOC standpoint, creating runtime based forensics detection here. So that's just one example here. We're going to go ahead and kill our stager here because we don't want to do anything else with it here. So as part of our final portion of this demo, I'm going to kill the PCAP because we captured so much of it, and we're going to make sure that we can detect something, right? We can detect something from our packet capture here. So we have Suricata, we've already updated rules, and we're going to go ahead and, whoopsie, we're going to go ahead and run and get the logs in this directory that we're running in. So Kali, paste it, use our live demo PCAT that we just used, and it's going to run. Let's give that some time. We're going to close Covenant, kill that off. We don't need the web dev server anymore. We're going to kill that. And look at all the signatures it's checking out. And pretty soon we should see the alerts pop up. This might take a little bit longer just because it's relying on the packet catcher reader than it was just signature and CPU and thread intensive. At least from a small little Kali box like this. Here we go, 2,500 alerts. Wow, that can't be good, right? So something isn't really tuned, but EVE JSON has its log flows, but we have fast.log here, so we're going to tell the last 10 fast.log entries here and see what we've got. That's not exactly what we're looking for, but let's take a look at grepping that. So let's look for PE. Let's try malware. Well, that's kind of interesting. And what we see is just invalid checksums all over the place. So that is not necessarily what we saw last time in these other demos, but fortunately we should have a copy of those those alerts that should trigger. Yep, and we've done the same thing in the past, and so we see a bunch of WebDAV items in there, and we should also see it's just examples here. So it does work. It's just that one of those things where depending on what it decided to showcase and how you close the TCP stream sessions and how you ran everything, um, it should show you multiple alerts based on your rule sets. So let's try to run that one last time here. Just for the sake of let's run that from, because you should have seen at least at minimum the buffer overflow here. Let's try something a little bit smaller here. And if nothing else, we're going to run it exactly on something else here. So, but one other tool I wanted to show you was Kappa. And Kappa Linux is from the Flare research group from Mandiant. And you can actually run it to evaluate binaries from a 132 perspective. So I'm going to evaluate our, let's say we're going to evaluate the grunt stager. And it's really nice because it gives you a lot of interesting items based on what it's capable of. And it's a .NET module and it may not run that. All right, so it doesn't appear to support that, but we can always run it on something else. So let's run it on, our M17 exploit, huh? How about that? I never copied it over. All right, let's copy this over real quick. All right, so you guys gotta bear with me. It's a really late night over here. It's roughly like 1 a.m. So I'm gonna run Linux and we're gonna run it against our what am I back into MS17? I'm gonna run it against our MS Venom kind of thing here. So let's go ahead and run that. Kappa Linux against our MS17 payload that we ran in Venom. And it should come back with stuff. Looks like our packet PCAP file is still showing the original here we go. It's just showing all these items here, but it's showing the DNS update intervals. Let's look for anything that has 443, right? And it's still showing invalid packet payloads. Let's try 445. And we shut down stuff. We should at least see the buffer overflow. There we go. Overflow attempts and all kinds of stuff. So we did trigger a whole bunch of stuff. We just need to look for what we're looking at inside and parse through those logs of the alert file. And this complains if it's packed, which is kind of interesting. So we can actually go back to another binary, which is, some of the limitations of some of these tools. Like I said, you need to use, other analysis techniques. So we'll copy Kappa Linux. And it's a good thing we have other demonstrations. So Kappa Linux, we'll just use my evil payload.exe. And see for the sake of verbosity here. I apologize in advance for that Siricata issue last time. I forgot what the signatures actually stated. So we see a set of 132 regular binaries, and it gives us all kinds of neat little instructions and anti-debugging capabilities. And those are forensics that IOCs you can find from a binary standpoint, and anything that you see here from a string standpoint that it's interested in, you might be able to extrapolate some of this for for your YAR rules and whatnot. So that's about it, guys, for today. I hope you enjoyed seeing a little bit of what we go on with when we do a purple team engagement, some of the items that we saw from a testing engagement on our pen testing as well as our purple teaming. And if you have any other questions, feel free to reach out to me, um, directly at contact@scisecurity.com, or find me on LinkedIn for Dennis Chat for our CISO, scisecurity.com again. Further reading here, just take note of these. We'll send this out in the deck. If you ever wanted to see what we were talking about earlier and a little bit more in depth and how that was exploited and why and, the ins and outs of it, you can certainly do so. Have a great day and thank you for watching.